Watch a sterile, rocky expanse. Within an accelerated geological timeframe, biological forces capture the surface, layer organic material, and construct a dense biological network. Ecological succession is the gradual and directional process of change in the structure and composition of an ecological community over time. In 1916, ecologist Frederick Clements established the core vocabulary for this timeline. The entire sequential progression is called a SER. The initial colonizers are the pioneer community, and the final, self-perpetuating state is the climax. The trajectory of a SER depends on its starting substrate. Primary succession begins at absolute zero, occurring in environments with no organic matter, no functioning soil matrix, and no residual seed bank. When a massive geological event like a retreating glacier scrapes the earth down to bedrock, it leaves behind sterile stone stripped of biological legacy. We see the same reset in a fresh basaltic lava flow. The new geological substrate is impermeable and barren, providing no organic material for colonization. Secondary succession is a recovery process. Here, a previous community has been destroyed by a disturbance, but a critical biological foundation remains. Following a fire, surface biomass is eradicated, but the vital subterranean architecture, the established soil matrix and dormant seed banks, survives beneath the ash. Because secondary succession relies on this surviving architecture, it progresses faster than primary succession. It avoids the thousands of years required to biologically manufacture a soil matrix from raw bedrock. The primary driver of these timelines is autogenic succession. In this model, the biological community physically modifies the environment to facilitate the next chronological stage. This cross-sectional diagram maps a lithosere, succession beginning on a dry, bare rock substrate, such as the granite of the Deccan Plateau. The mandatory primary colonizers in a lithosere are crustose lichens, which adhere directly to raw mineral surfaces. These lichens secrete organic acids to chemically weather the rock. As they die and decompose, they synthesize the ecosystem's first microscopic layer of soil. Contrast that with a hydrosere, representing succession in an open aquatic habitat, like a pond in the Gangetic Plains. The initial seral stages are aquatic. Microscopic phytoplankton populate the water column, eventually generating enough organic detritus to allow submerged vegetation to take root in the benthic zone. As sediment builds, the habitat advances to a rooted floating stage featuring plants like the lotus, followed by an emergent reed swamp stage at the water's edge. The mechanical driver of the hydrosere is sedimentation. As sequential generations of aquatic plants die, their accumulating organic matter physically fills the basin and shallows the water level. This rising sediment levels the habitat. The aquatic ecosystem transitions into a marsh meadow, which eventually dries enough to support a terrestrial woodland canopy. Whether starting on dry rock or open water, autogenic biological activity drives the habitat toward a stable terrestrial equilibrium. We can observe these stages in sequence, but what is the exact mechanism that causes pioneer species to cede territory to the next wave of life? In 1977, ecologists Connell and Slatyer categorized this species replacement into three mechanistic models. The facilitation model represents the classical Clementsian view. Here, early colonizers modify the soil and habitat to support the establishment of the organisms that will eventually replace them. The transition from soil-building lichens to deeper-rooting mosses provides a definitive example of biological facilitation. In the tolerance model, later successional species establish themselves without pioneer assistance. They succeed because they can tolerate lower resource levels than the earlier colonizers. We see this when shade-tolerant tree seedlings germinate beneath full-sun pioneers. They grow slowly in the shadows until they overtop and outcompete them. The inhibition model describes a different dynamic. Established early colonizers actively resist invasion, blocking the establishment of later species through resource monopoly. Under the inhibition model, succession progresses only when occupants are damaged by external disturbances or natural mortality, creating an opening for new arrivals. The path toward a climax community involves competitive exclusion and opportunistic timing. To understand why succession eventually stops, we must shift the analysis from species composition to energy flow, as formalized by E. P. Odum in 1969. Odum characterized early developmental stages as realms of R-strategists, organisms optimized for rapid growth and high reproduction within simple, linear food chains. As the ecosystem matures, the fast-growing R-strategists are replaced by K-strategists, large trees and mammals integrated into complex food webs and closed nutrient cycles. This graph charts gross primary productivity, or GPP. Early pioneer plants capture solar energy rapidly to build new biomass. The red line tracks respiration. Because the early biological structure is simple, the metabolic cost of maintaining that biomass is low. Because GPP vastly exceeds respiration in this stage, the system generates massive surplus energy, known as net ecosystem productivity. The respiration curve now climbs drastically. The ecosystem must spend significant energy just to maintain its multi-layered biomass. At the climax stage, we reach a thermodynamic intersection. The ecosystem's total respiration cost matches its gross primary productivity. In Odum's model, as GPP and respiration reach parity, the net ecosystem production of a climax forest approaches zero. A mature ecosystem functions as a self-regulating engine, shifting its energy use from biomass expansion to structural maintenance. We define the climax community as the self-perpetuating endpoint of a CSIR, adapted to a specific set of climatic conditions. Clements introduced the first rigid framework for this endpoint in 1916, the monoclimax theory. Clements argued that succession is strictly deterministic. He believed any given regional climate would inevitably produce one specific climax community. In 1939, Tansley proposed the polyclimax theory, rejecting this single deterministic outcome. Tansley's framework allows for multiple stable endpoints within a region, dictated by local variables like soil chemistry or slope that override the general climate. A pyroclimax is one such example, where periodic fire permanently maintains a grassland, preventing a forest climax from ever forming. Modern ecology relies on Robert Whittaker's 1953 climax pattern hypothesis, which moved away from discrete, boundaried communities. Whittaker detailed a continuum concept, where ecosystems are fluid, overlapping gradients. Individual species respond independently to shifting environmental resources. Succession operates as a perpetual thermodynamic negotiation between living organisms, stochastic disturbances, and the physical limits of the environment.